Okay, so today we're going to be covering fatty acid synthesis. Oh my gosh, I have recorded this voiceover so many times. I'm losing it. Um, but anyways, I don't want to make it super long because this first clip is 4 minutes long and I went overtime trying to explain the first step of fatty acid synthesis, so I'm going to make this very short and brief. Pretty much the layout of this video is going to be like a study with me. I'm going to learn the content, try to teach it to you so I can study better because I have a final coming up and I want to know the content for the final. But pretty much I did a layout of what we're going to be doing today or covering. So fatty acid synthesis starts with the transportation of acetyl-CoA into the cytosol, followed by NADPH formation, as well as malonyl-CoA, malonyl-CoA synthesis, and then butyryl or butyryl. Okay, the 4 carbon ACP synthesis, and then elongation, and then finally desaturation. So yeah, that's pretty much the layout. This first clip is just me doing a layout and then starting acetyl-CoA transportation, and then I do a time lapse, and then I do a final kind of overview of the board of what I've written, my handy dandy whiteboard. Um, so yeah, let's start with the transportation of acetyl-CoA into the matrix. Okay, so the first step is to get acetyl-CoA into the matrix. Sorry, not the matrix, the cytosol. Oh my gosh, did I say that wrong the first time? I'm gonna edit that. But the acetyl-CoA needs to get into the cytosol because it's currently in the matrix. The problem is the inner membrane is very impermeable, so it's kind of like a very tight border control, or not border control. You know, you know when you're at the airport and you can't bring water bottle, or you can't bring water like on the plane, so they make you dump it out, or you're just it gets confiscated. It's kind of like that because the inner membrane is very specific in what can cross into the cytosol from the matrix. So acetyl CoA needs to be converted into a form that is allowed to cross the inner membrane, and this is going to be the molecule of citrate. So citrate is a molecule that we will see in the TCA or the CAC, whatever you call it, and can cross the inner membrane. And so to do this, it's converted into citrate by citrate synthase. Um, and so once it's converted into citrate, citrate crosses the inner membrane into the cytosol and can then be converted into oxaloacetate. Um, and we've seen this before in gluconeogenesis. But oxaloacetate, once citrate is converted to oxaloacetate, acetyl CoA is regenerated. This requires an expenditure of ATP. Um, and then from there, oxaloacetate can be converted into malate. Malate can then cross the inner membrane once more and then can be converted to oxaloacetate, which can be converted into citrate. So basically, you can just do the whole cycle all over again. But before crossing the inner membrane, malate can actually be converted into pyruvate, and from there you form NADPH. So NADPH is pretty much what is like one of the two things that are required for fatty acid synthesis, with one being acetyl CoA and then NADPH being the second, because that's kind of like um, that's the oxidizing cofactor, if that makes sense. So yeah, that's pretty much the first step is to transport acetyl-CoA into the, I said matrix, it's supposed to be cytosol. Oh my gosh, that's so embarrassing. That's pretty much the first step. So the only thing with this first step is that this is only done when there is an excess amount of citrate into the in the matrix. If there's not an excess amount, then citrate will be used for ATP production, as in oxidative phosphorylation and just all that kind of stuff. As I said, NADPH is required for FA synthesis or fatty acid synthesis, and this is only done when citrate is in excess. So yeah, so the next step is, oh my gosh, what was I gonna say? Malonyl CoA synthesis, or as known as malonyl ACP. Excuse my pajamas because I decided to change it to something comfy, and then I wore a hoodie because my room is always freezing cold. But anyways, let's get started with malonyl-CoA. Malonyl-CoA formation occurs with the enzyme acetyl-CoA carboxylase, which basically has three domains. The first domain is biotin carrier protein domain, second domain is biotin carboxylase, third domain is trans-carboxylase. So what happens is biocarbonate will be attached to the biotin carboxylase domain, and the biotin arm, which is attached to the biotin carrier protein, latches onto bicarbonate, and this is an ATP dependent reaction. And so the biotin carrier protein will activate the incoming bicarbonate by attaching a nitrogen atom, which is in the biotin ring. That's why it's an ATP dependent reaction. So the biotin ring will swing its arm, or I guess the lysine side chain, and we'll move it to the other domain, which is the transcarboxylase, which transfers the activated carbon dioxide, so the carbon dioxide in bicarbonate, to acetyl-CoA, forming malonyl-CoA. So the next reaction occurs with malonyl-CoA and then acetyl-CoA, another acetyl-CoA. And this is catalyzed by the fatty acid synthase complex. And so this complex has 7 domains, which 6 of them have enzymatic activity, and then the other one has acyl carrier protein, which is your ACP. So what occurs between malonyl-CoA and then the acetyl-CoA is a condensation reaction driven by decarboxylation. So the malonyl-CoA will lose a carbon dioxide in the process, and that will form a kind of 4-carbon molecule that needs to be reduced, because right now it's in its fully oxidated form, because it has two carboxyl groups. So now the second step is a reduction reaction. So NADPH will be oxidized to NAD plus, and so this reduces the 4-carbon molecule into a tertiary alcohol. So the beta carbon in this 4-carbon molecule will have a tertiary alcohol in it. The third step is a dehydration step. So this tertiary alcohol will be turned into a alkene. So what happens between that beta carbon and that alpha carbon is that you'll lose a hydrogen, and then you'll lose a hydroxyl group. So then you will get a double bond between your beta carbon and your alpha carbon, and that's 4-substrate molecule. The last step is you're going to do a second reduction, and this will involve another molecule of NAPDH being oxidized into NAD plus, and so you're going to reduce your alkene into an alkane. Once that alkene has been reduced into an alkane, you have now formed butyryl CoA, or known as butyryl ACP. So at this point in the process, we have used 2 molecules of NADPH, so it's very important that you pay attention to how much we need, or kind of why we're generating this, because it is used for fatty acid synthesis. Okay, so for the next process is elongation. So we're just going to take that butyryl ACP and kind of add more carbons onto it. And to do this, we need to move the butyryl ACP to the Ks domain and kind of link it to that thioester. So where the acetyl-CoA group was before, we're just going to link the butyryl to it. So the enzyme is kind of going to curve its arm, and then that linkage will form between the thioester and the butyryl ACP. So by moving the butyryl to the Ks domain, you're able to add a new malonyl group to the ACP domain. And so the next step would be a condensation reaction. So it links all the groups together on that ACP domain. And of course, the condensation reaction will have carbon dioxide phased out or removed from the reaction. So now you're going to go through the whole process again, where you have a reduction, a dehydration, then another reduction to get a 6-carbon fatty acyl group, which will be hexanoyl ACP. And so your methyl carbon will come from the acetyl-CoA group, and yeah, you're lengthened by 2 carbons. So this whole elongation process will just keep continuing over and over again until you have a 16 carbon chain. And so now I'm going to talk about what happens when you have a 16 carbon chain. We're going to go into desaturation time. So yeah, so after you get to the 16 carbon chain, the saturated fatty acid palmitate, you're going to go from palmitate to palmitoic acid. And this is by having a cis double bond at carbons 9 and 10. So this is done through simultaneous oxidation reactions. So NADPH is oxidized to NAD plus. So the electrons from this reaction are transferred to FADH2. So from there, FADH2 is oxidized to FAD. Those electrons are transferred to Fe2 plus, so iron 2 plus, which then reduces to iron 3 plus or Fa3 plus. So that allows the fatty acyl CoA desaturase, which is the enzyme that catalyzes this reaction from a saturated fatty um, acyl CoA to a monounsaturated fatty acyl CoA. So this enzyme, fatty acyl CoA desaturase, is going to be reduced from this reaction, and now it can interact with oxygen and the fully saturated acid. So at this point now you have a double bond formed between carbons 9 and 10 that gives you the abbreviation 16 colon 1 delta 9. That's because you have a, what's it called? A double bond between carbons 9 and 10. We also, like mammalian cells, also have a desaturase for 5 and 6, or carbons 5 and 6. But like we cannot introduce additional double bonds past 9, just because the like our bodies don't do that. But if our bodies do have polyunsaturated fatty acids, which does occur, it's just because we have introduced them into our diet. So what we've eaten, so let's say like French fries or anything like that, we have introduced more double bonds than what we typically make. And that's it.